So folks, let's just do a couple more of these function composition problems. So here I'm asking you to find h composed with j of the number 5. I want you to do this two different ways. So the first method is kind of the more useful method, but it is the long way around the barn for this particular problem. That is, I'm first going to find h composed with j of x. Now you should always, folks, sometimes people get a little bit sloppy with their math. You should always pay attention to the difference between when I'm talking about a function versus when I'm talking about plugging in, evaluating a function at a specific input value. So the first thing I'm going to do is I'm going to find h composed with j of x in the method that I did above. So what I'm going to do here is I'm going to say, well, h of x is the function, the square root of, and then it's whatever my independent variable is, minus 9. That's my function h of x. It's the square root of the independent variable minus 9. But I'm sorry, let me backtrack just slightly, folks. Sorry to do this to you. I'm going to rewrite this first as h of j of x. That's the definition of function composition. So it means to take the function j of x and compose it inside of, or put it inside of the function h of x. So now I'm going to repeat what I had before here, folks. So what was h of x? It's this function where we take the input independent variable, whatever it is, subtract 9 from that independent variable, and then take the square root of it. And what we're going to do is, in place of the value x, we're going to put the j of x, that function, in place of the independent variable there. So there's my j sub x. Well, what is j of x? The definition of j of x is that it's x squared. And so now I've got the composition of these two functions. I've composed one with the other. By the way, it's worth pointing out, folks, because I've seen students make this mistake all the time. This is the first instance I've seen it in our Math 1440 pre-calculus class anyway. This does not equal x minus 9. Okay, so careful. I've seen students say that all the time. Usually they don't say it in such a simple example, but they'd maybe do it somewhere else. So I just want to warn you, square roots do not distribute over addition or subtraction. Okay, so with that warning out of the way, let's go ahead and finish this problem. We weren't asked to find h composed with j of x. We were asked to find h composed of j of 5. So let's actually do that. H composed with j of 5 is equal to, now I'm just going to take and plug as my independent variable 5 into this function. So it gives me 5 squared minus 9, and I can clean that up as the square root of 25 minus 9, or the square root of 16, which is equal to 4, and I've answered the question. The second way, by the way, I sort of prefer this method because notice what I have. I now have a tool. I've actually built the composition function, because now if the problem changes to find h composed with j of 21 or 19 or pi, I can still just plug those independent variables into this composed function. If I choose to do it this way, where I'm going to do a two-step procedure, there's nothing wrong with doing this two-step procedure, but it just goes a little bit, it just means it's not quite as versatile. So let's go ahead and actually find it using the two-step procedure. So first of all, I'm going to compute j sub 5. If I were to compute j sub 5, that would be 5 squared, which is equal to 25. Then I'm going to compute h of 25, which is equal to the square root of 25 minus 9. And when I do so, that gives me the square root of 16, which is 4. Notice in the end, I arrived at the same answer, either method. What's going on here? Well, the picture that goes with this, and I should have given you more room for this, folks, and I apologize. The picture that goes with this is that we have two functions. And this first function, the innermost function, which is j of x, takes values from here, like the number 5, and it maps the number 5 over to the number 25. It squares it. So that's what my function j of x does. Well, then what we're asked to do is we're asked to, because 25 is in the domain of h of x, maybe here's the domain of h of x, we're going to take and we're going to map the number 25 in the domain of h of x, and we're going to map it to the number 4 through the function h of x. So here you can see that what I've just depicted here is that two-step procedure for the function j of x and the function h of x. So we took the domain value 5, we evaluated it through j of x, which mapped it to the number 25. Then we treated 25 as an input that we then plugged into h of x, and we looked at where the function h mapped it to, and that's where we got the number 4. So this procedure, the first one I did, whereas where we actually built the composite function, the way that works is we actually build a function that will in one step take us from the domain value 5 over here in the domain of j of x and map it to this number 4 over here in the range of h of x. And that's the procedure of doing j composed with h of x. Folks, sometimes you'll see parentheses around the composition, sometimes not. I sort of like to do that, but you don't have to. Folks, I have an error here. This should be j composed with h of x. We have to be very careful here. Nope, I just rewrote it. Sorry, folks, getting a little tired here. This would be h composed with j of x. I'm so sorry to have gotten that incorrect, folks. We always work function operations from inside out. So we do closest to, when we write this by terms of its definition, h composed with j of x, we would do this as h of j of x. So the first step we have to do is go to j of x and then to h of x. So this is the image that helps to explain what we're doing here. What I'd like you to do then is I'd like you to go ahead and try this yourself. I'm going to get you started because I just made that silly error of getting the order wrong. So I'm going to get you started with this. In this case, the first way you could do this is find j composed with h of x. What is that? By definition, that is j of h of x. And so to get you started, let's see here, the function j of x is the squared function. So there's that squared function. Let me color code this. I'll go ahead and make this in blue. This was our h of x. So I'm going to take the function h of x and square it. Okay. So I'm going to let you finish this. And if you have any questions, please come by and see me. Okay, so let's practice that again here. I'm going to do number 5 on my own, and then I'm going to leave you to do, or I'm going to do number 5 with you, and then I'm going to leave you to do number 6 on your own. Okay? So, folks, I botched that explanation just slightly, just very briefly at the end there, so I want to make sure we get this correct. We've got the domain of my my innermost function here, which will be my m of x. Let me just clarify. This is asking us to find n of m of x. So my innermost function is this m of x, which is the cosine function. So we've got this cosine function, which is going to take an input value and map it over to some output value. Then we've got this natural log function, which has its own special domain, and it's going to map to its particular range values. So this will be our n of x function. So let's go through this. What we're asked to compute here is n of m of 2, or of 2 pi, or n composed with m of 2 pi. So let's go ahead and give this a shot. The first way we're going to do this is n composed with m of x is what we're going to compute first. So we're going to find it as a function. That is, I'm going to find the rule that's going to take this same, here's this value, 2 pi sitting right here, and it's going to take 2 pi and in one step do both operations. That's going to be our composition step. So n composed with m of x. Okay. So let's give it a shot here. What does this mean? By definition, this means to take, I'm going to zoom in on that a little bit. What does this mean? By definition, it means to take n of m of x. So I'm going to take the function n of x, which is my outer function. That's the natural log of my independent variable. And in place of my independent variable, let me color code this again. m of x. In place of my independent variable here, I'm going to put the function m of x. Well, that is the natural log of, what is m of x? It's the cosine of x. So there I've taken the composition of these two functions. Now I can go ahead and evaluate m of x. That's equal to the natural log of the cosine of 2 pi. Well, the cosine of 2 pi is 1, so we're left with computing the natural log of 1, which is 0. So the picture that goes with this, folks, is that we're going to take the number 2 pi and we're going to map it. We're going to map it to this value here of 0 through function composition. So that's one way of doing it. The other way of doing it is the two-step process. So here we're going to first find m of 2 pi, which is equal to the cosine of 2 pi, which is equal to 1. So this is going to become the input into my second step. So we're going to find n of 1, which is equal to the natural log of 1, which is equal to 0. So if we imagine this is a two-step procedure, first of all, our m function maps 2 pi to the cosine of 2 pi, and the cosine of 2 pi is 1. And then our n of x maps the number 1 to the number 0, where our n of x is the natural log of x function. So hopefully that's helping to clarify this composition. This will be a little bit challenging if you are very rusty on this. If you're finding it difficult, please again just come by and see me. I'd be happy to give you some more explanation on this. Okay, so I'm going to leave it to you guys to try number 6 on your own. I will give you one hint. And my hint for you with this is that if you were to take the natural log of e to the m, that just simplifies through my identity properties to the number m. Okay, folks, that's the end of this video. I hope to see you shortly in class. Good luck, and if you have any questions, let me know.